Hello, everybody. I just wanted to go over gravitation notes for you, with you. As you watch, you can listen and write down everything that's highlighted in yellow. So we're starting off with this slide, gravitation. So I'm just going to go through the slides, talk about them a little bit, and then I'll show you how to do the calculations in Desmos or on the provided textbook calculator. So we're talking about gravitation. There's Isaac Newton. This is one of the main things he's famous for, besides Newton's laws, right? Um, and this is the formula for gravitation, universal gravitation. So any two objects um, will have a force of gravity between them. Even like these two pins, they have a gravitational force between them um, due to gravity, but the the force of gravity between the pins and the earth is stronger. So instead of falling together, they fall down, right? Attracted to the earth. But there is a perceptual that you can measure the force of gravity between them. We can't feel it because we aren't that sensitive. But yeah, any two objects should have an attraction. So this really comes into play with planets, things that have very large mass, because the universal, the gravitational constant, this big G, is very small. So you need very large masses to make it perceptible. Now the pins are very small. That's why their masses are small. So you can't really feel that. But when you get something as big as a planet, you have that mass, then you can feel gravity. Like we feel the gravity from the Earth because the Earth is very massive, right? And we're far away from its center. Um, so yeah, so then you'll get a perceptible gravitational force. So this gets into, so we're talking about circular motion. Well, how is falling like orbiting? Well, so a satellite or a moon or a man-made satellite, it goes around the Earth. And how does it do that? Well, if you take a cannon, and so you see we're shooting here, we shoot a cannon at 2 kilometers per second, a low velocity, it's going to arc and come down. If you do 4 kilometers per second, it's going to arc and come down. If you do 6 kilometers per second, it's going to arc and come down. But once you hit 8 kilometers per second, the curvature of this matches the Earth. So it never hits the ground. It never arcs down. It's moving so fast that it's just constantly falling. So that's kind of cool. I like that. I had never really thought about that before, about how the moon is it's in a gravitational field with the Earth, and the moon is constantly falling towards the Earth, but it never hits it because it's orbiting, right? And that's an orbit. So orbiting is like falling. All right, here's the law of universal gravitation. Newton said that all objects are attracted to each other with a force called gravity. Here's an explanation. There's a force of attraction between any two objects in the universe. So here's the force. They're attracting each other. So each one is pulling on the other with the same amount of force. And this force is based on the two masses, right? How far apart are they? And the universal gravitational constant. So the bigger the m's, the bigger the force. The bigger the r, the smaller the force, right? That's a inverse relationship. So there's a proportional or direct proportion with mass and force. There's a inverse relationship between r and f. So the bigger the r, smaller the f. The smaller the r, so the closer things are, it's kind of like a magnet. The closer they are, the bigger the force. The direction of gravity, the force of gravity is always attractive. The force is directed along a line that connects the centers of the two objects. What is G? It's the gravitational constant, and it's the same everywhere in the universe. So any planet, we can calculate gravity with this gravitational constant. Scientists don't know why it has this value. It's kind of like pi. It's just one of those constants that we discover, and it's everywhere. All right, so then we get into the examples, how to calculate. So you could use this calculator, which I'll provide a link, and I'm going to give you some practice problems next time. But notice how they use the E here. So this is scientific notation. So when we do the practice problems, you can see that 5.98 E positive 24 is the same thing as 5.98 times 10 raised to the 24. They just use this E function this E function takes the place of this times 10. So they mean the same thing. So it's an uppercase E, sometimes it's a lowercase e. So it's the same thing. So whenever, if you see a scientific notation, like this one, 6.38 times 10 to the 6. So this is going to be 6.38 E6. So those are the same. So that's how you have to enter these here. So we could do that. Let's see. So let's do this problem in the textbook calculator and Desmos. So what is the force of gravity between Earth and a 100 kilogram man standing on the Earth's surface? The radius of the Earth is 6.38 times 10 to the 6. So let's do that. Sorry, it's late. Let's do the calculator first. So we got the 100, we got the mass of the Earth, we got the distance between them. So when you put those in, it does the formula for you. It even squares the distance for you. So we got 980.35. So you could do that here. Or you could do it in Desmos. So in Desmos, you just put in, I would put parentheses on top, 6.67, and instead of the E, I do times 10 raised to the negative 11, and I push the right arrow times 100 times 5.98 times 10 raised to the 24th power divided by 6.38 times 10 to the 6. And this one, I'm going to do parentheses as well. 6.38 times 10 raised to the 6. Oops. Raised to the 6. And then I have to square this thing. Raised to the second power. And then you see I got 979.9, which is the same thing as 980. So very similar. If you put any one of those answers, those will work. All right, and then there's another problem. Calculate the force of attraction between the Earth and an alien spaceship orbiting at a radius of 20,000 kilometers. Earth's mass, spaceship mass. So they give us the 20,000 kilometers. So we need to put that in meters. So you just add an extra 1,000. Right. So because it has to be in meters, everything has to be the same. So if we do this, universal gravitational constant is always the same. We got the mass of the Earth. Mass of the spaceship is 500,000. And the distance between them is 2 E. So you can use this E here, and it's a positive 7. E7. All right. So I got 4.99 times 10 raised to the 5th. So let's see if I can do that in Desmos. So I'm just going to copy this. And then just change the numbers. 500,000, is that right? Mass of the Earth, that and that. 2 times 10 to the 7. All right, so I got there 4.98 times 10 to the 5th. So same numbers. I wrote them both in the notes. So same answers. It works. So that's how you guys can do these problems. And so next time I'm going to give you some more problems to work on. Today it's just the notes and that practice and the vocabulary. Okay. So just notes and vocabulary today, since I'll be at school tomorrow. The last couple of slides, that's the one we just did. And then this one's just talking about how gravity controls the planets. All orbital motion is due to the force of gravity. The force of gravity provides a centripetal force that keeps satellites such as planets moving in circles or ellipses. What is a satellite? A satellite can be natural or man-made. Satellite orbits a more massive object. Example, Earth is a satellite of the sun. Earth's moon is a satellite of Earth. And there's hundreds of man-made satellites that are in use in GPS and communications. Let me see if I can find that real quick. Satellites orbiting Earth. It's pretty crazy how many there are. $19,000 satellites orbiting Earth. Junk, not junk. All right. So yeah, these are all satellites. So you can see the orbits of all these satellites, all those little white things. 19,000. Like they're moving. Anyway, so I just wanted to show you that. So all those things are orbiting, so we need to keep them up there, right? So that's what a physicist does. That's part of their job, right? Okay, so that's the notes. So like I said, just do vocabulary, copy these notes down, read them, write them, think about them. Try the Desmos and the calculator. And next time we'll do some practice problems. Have a good night. Have a good day.